Okay, so we have a speaker, Karina Mauco, and Ilaria, would you like to introduce?
All right, yeah, I'm happy to do so. So today we have Karina Mauco. She earned her PhD at UNAM. I'm trying to pronounce it in Spanish. Let's see, Universidad Nacional Autónoma de Mexico, something like that.
Yeah.
And then she moved at ESO in Munich as a postdoctoral fellow, and she's working in the Wanda project, which is a ERC grant by Carlo Manara. And it's focusing on understanding the evolution of planet-forming disks in IMAS subforming regions. And today she's going to tell us about the Orion in particular.
Yeah. You know, I read just a few joke. I used to see Karina only from the Zoom screen. It's really great to see her here. And then I think the Jesus and the Nuria, I don't know if they joined, but she was a student of them.
Yes.
So I just wanted to mention that. Yeah. Okay.
Yeah. So, well, first of all, thank you a lot for the invitation. It's really, really nice to finally be here and meet in person, all of people here working in the same thing that I'm interested in. So it's very exciting to be here for the first time. And hopefully this will, drive a lot of discussion and collaborations and just doing great science. So, as they say, I'm working right now in Orion, so testing external photoevaporation using optical forbidden lines. So, okay. So first of all, a little bit about me. So as Ilaria said, I'm a MUSE postdoc in Garching since December 2023, so last year. And I work in the Wanda, our ERC grant. Wanda means winds and these structures near and far, so you can for the title, see that we are really interested in this evolution and how these winds that are now gaining more and more attention for driving this evolution connects with substructures in the disk. And you can see that the Wanda team is composed of 2 postdocs, so Justin, Campbell White, and me, and also 3 more PhD students. This is led by Carlo Manara at ESO. And the part that I'm working on in this Wanda team is in the forming planets in massive star-forming regions. So that's why I'm interested in the impact of external photoevaporation in protoplanetary disks. So I'm going to be talking about that. So the motivation real quick of why this work is important. Well, we know that protoplanetary disks is where planets form. So we know that it's very important to study and to try to understand the evolution of these disks if we really want to understand how our solar system formed, how Earth formed. And we know that in the standard picture, the viscous paradigm, this evolved because, there's accretion, so material coming from the inner part of the disk to the star. And we know that this sometimes produces collimated jets that has been widely studied in emission lines at 100 kilometers per second. But we also know that they also lose a lot of mass through winds. And the winds in the protoplanetary disk came in 2 flavors. So we have the magnetodynamical winds, so image the winds that are usually related to the inner disk and has gained a lot of attention as a driving of accretion, because we know that now the MRI is not that effective in most of part of the disk. So now the image winds are really key to try to understand if they're related to accretion and to the evolution of these disks. But we also know that there's also these thermal winds, so the photooperating winds that are produced by the irradiation from the star, from the UV and X-ray irradiation, that is also producing these photooperating winds that can also be significant in the mass loss, because that is a key parameter that we want to constrain, right? The mass loss in winds, so we can know the time left for planets and how that affects the evolution. But we also know that these protoplanetary disks are not formed in isolation. We know that if they are in the cluster environment, they have this massive star. So the feedback from massive stars, the high energy photons coming from this massive star can also produce this type of winds. So it's very important to also study that. So how do we know more about these winds? So we go to optical and infrared wavelengths because we can there characterize the atomic component of protoplanetary disks, and particularly we go to wind and outflow tracers. So the optical forbidden lines, which are the ones that I'm going to talk most during this talk, because the idea is try to identify gas lines at a higher resolution, higher enough to really detect the shift in the velocity of the line compared to the Keplerian motion of the star, around the star. But also, if you go to longer wavelengths, those 2 millimeter observations, now that we have these surveys of protoplanetary with ALMA, for instance, or the BLA, we can also start looking at this connection between the inner, what is happening in the inner disk with the outer disk, and also how that relates, and try to understand these dispersal mechanisms in a better way. So the bottom line is that if you really want to understand the evolution of protoplanetary disks, you really need to determine the properties of these disk winds and the mass loss in the winds. And that's what I'm going to be talking about during this talk. So what do we know about these winds? There's have been a lot of efforts in trying to understand these winds from the optical wavelengths. The key question here, which is still an open question, is what is the origin of these winds? So we don't know exactly if the forbidden lines here are coming from an MHD wind or for a thermal wind. And that is important to know because that's really constrained the mass loss rate. They are different if they have different origins. But from all of these now, like more than 20 years of studies of this line, particularly in the optical wavelength, we use the oxygen 1 line, so at 6300. And from all of this work, we certainly know that this line can come with different components, the oxygen 1 line. We have the high velocity component here at 100 kilometers per second, and we know that that is tracing the jets and the outflows that come from the accretion process. That there has a lot of consensus that that is where the origin of this high velocity component is. Now, for the low velocity component here, that is close to the velocity of the star, it's more tricky. We don't really know what is the origin of this low velocity component. There has been a lot of effort in trying to understand that, and there seems to be a consensus now that at least the broad component, because you can see here that this line, this low velocity, sometimes come with these two components. So the broad component, which is the full width had maximum of this line larger than 40 kilometers per second, more or less, and also the narrow component. So there has been a lot of more consensus that the broad component is related to an MHD wind, or at least to the base of the MHD wind. But for Basanti 2019, further argue that the whole low velocity component, so the broad and the narrow component, trace like a similar mechanism, so a radially extended MHD wind that fits a jet. And that was based on the finding that the kinematic components of the broad component, so the full width maximum and the peak velocity, that is what we measure, are related to the properties of the narrow component. And in turn, also related to the equivalent width of the high velocity component. So they say that they trace the same thing, but more recently, in 2020, Weber argued that, in fact, these photoevaporative, these optical forbidden lines can be reproduced by the combination of MHD wind that is producing the high velocity and the broad component in the inner disk, plus a photoevaporative wind producing the narrow component. So you can see that we are more certain that the high velocity and the broad component has an MHD wind origin. But for the narrow component, we are still not quite sure. Of course, we need more observations and probably new techniques, as pointed out by William, 2021, using spectroscopy. We know that at least for one source, which is Orion loop, the narrow component in the oxygen 1 low velocity component is definitely related to an MHD wind. So this is still an open question. And of course, there's a lot of interest in trying to study this type of line, but this is only using the optical wavelength. So if we go to the infrared, yes.
Question. So for the Wayland result you're describing,
Yes.
The evidence that it's an MHD wind, is that just based on where it's coming from, or is there another?
Yeah, it's just based where it's coming from. It's really close to the.
Yeah.
Oh yeah. Yes.
So what happens is that the velocity is certain. So with spectroscopy, we measure the shift, right, with respect to the continuum. What happens is that at 2 AU on this mid-plane, the speed is 30 kilometers per second, and you can get that from propagation, just too fast.
Okay, it's okay. And you know where it's coming from, because it's effectively resolved.
Mm-hmm. Yeah. So if you go to also longer wavelengths, so the infrared, there is this neon 2 line at 12.8 microns that we know that is also tracing as a slow thermal wind, and there has been a lot of effort in trying to study that line. We know that all of the Ilaria Pascucci in collaboration works in this line. And in this recent work from Ilaria in 2020, they studied this sample of protoplanetary disks where they combine optical and infrared observations of this sample, and they have a sample of full disks and also these with cavities. And what they found is that for the full this sample, they lack, or most of them lack, the emission at the neon-2 low velocity component. And they explained this because they also have a strong emission at the oxygen-1 low velocity component that is tracing an inner MHD wind. We know that this wind is mostly molecular. Only the atomic part that is being traced by the oxygen-1 line is the one that is producing this line. So this inner MHD wind is blocking the hard X-ray that can go to the other part and photoionize the neon-2. And that is something that it happens for the disks with cavities. So you have a weaker MHD wind because they usually have a weaker emission in the oxygen-1 low velocity component. So the hard X-ray can actually pass through the wind and photoionize the neon-2. So you can see that you expect a change in the emission lines in the oxygen-1 and also in the neon-2 if the disks have an inner cavity, if they with those superstructures. And also this was also confirmed in this very recent work from Haya 2024 and also with Ilaria, where they actually observed this source Ticha, which is a transitional disk. It's like a 20 AU cavity, and they observed with JWST, and they actually resolved this neon-2 line. They confirmed that the neon line comes from further away from the disks, and they also detect the argon line. And you can see how this multi-wavelength approach and having also more sensitive observations with the JWST can also give us a lot of information, and we can now start to characterize in a better way these winds that are coming from these type of systems. And what they found here is that the argon emission is more compact than the neon emission, and actually the wind proved by the argon line is photoionized by the EUV, while the X-ray is the one that can pass this wind proved by the argon and photoionize the neon. And in this case, the oxygen-1 line is related to the MHD wind in the inner disk. So you can see how these can really now, we can really start to characterize these winds and also get mass loss rate and all of that. So you expect a change in the oxygen-1 line if you have an inner cavity. So that was also proposed in this early work from Ercolano and Pascucci 2017, where you have this sketch where you know that if the disk is evolving in time and you start carving this inner cavity, even by planets or by internal photoevaporation, then you lose this inner part of the disk that is tracing the broad component. So you lose the broad component with time, and you end up with a single component of the oxygen low velocity component. And that was also something highlighted by Basanti 2019, where they also observed that. So you expect that you lose first the high velocity component and also the broad component in more evolutionary stages. So transitional disk seems to have this single component oxygen-1 line, and this shows a great example of how we can start to relate what happens in the inner disk with the spectroscopy, looking at these optical forbidden lines, with also ALMA observations in the radio and trying to see the structures of the disk. And that was also something highlighted in PDS-70 by Justin, this Campbell-White last year, where they studied the oxygen-1 line in PDS-70 and is, in fact, a single component in the oxygen-1 line. So if you expect a change of the oxygen-1 line with those cavity, you also expect a change with age. Because we know that at later evolutionary stages, internal photoevaporation, carving the cavity, is more prominent in these type of systems. So there has been a lot of effort also trying to study this chain of the line of the oxygen-1 with age. And here I show you some examples. So here are the kinematic properties of the oxygen-1 low velocity component for 3 different regions with different ages. So here is the full width at maximum on the y-axis and the peak velocity in the x-axis for these different regions. And you can see, as expected, that, for instance, Upper Scorpion here, which is the older region, 5 to 10 million years, you can barely see any high velocity component, which is the green points here. you lose that, and you also have very little broad components as well. So what we have known now, thanks to all of this study with age, is that you lose the high velocity component and also the broad component, and the single component of the oxygen one line become the dominant mode in other regions. So it's very, very interesting that you can actually start looking at these evolutionary changes in the oxygen one line of the protoplanetary disk by just looking at this line. But of course, all this work have been done in low mass star forming regions, and we know that most of protoplanetary disks and planets form in massive stars. So we also need to go and look for massive star forming regions, and that's where our work comes in. So I'm currently working external photoevaporation in this cluster, Sigma Orionis, in Orion. So it's an intermediate age cluster, it's between 3 and 5 million years. You can see here from the picture on the left that is very close to one of the Orion belt stars. And at the center of the cluster, it has this multiple massive OB system. So Sigma Ori here at the center, you can see here the spatial distribution of our targets. So Sigma Ori is here at the center, and the more massive star in the system is an 0.95 star, which is Sigma Ori. And you can see that from the strain of the FUV field at the really center of the cluster, so inside 0.5 parsecs in projected distance from Sigma Ori, you can have very high values of the strain of the FUV field, so 10 to the 4, 10 to the 5.
Yeah, did you include all the Sigma Ori because it's quadruple system or something?
Oh yeah, we check what was the impact of the other components, and really Sigma Ori is the old star is dominating everything. So it's basically that it didn't change if you just look and add the B stars here. So it's all done by Sigma Ori. Yes.
I mean, the Sigma Ori itself is multiple source, right?
Oh yeah, yes.
But we included everything as a Sigma Ori.
Yes, exactly. Yeah. So what we did was perform the first large scale survey that combines the spectroscopy and ALMA observations for the cluster.
Before you move on.
Yes.
Are any of the stars here in Gaia to give you 3D distances?
Yeah, that's
too extincted.
Yeah, that's a good point. It's not a problem of extinction for Gaia. It's a problem that the parallaxes for individual sources is very uncertain. The error bar are even larger than the projected.
Yeah.
But for the other YSOs, you can do that. It's just that their massive stars are too bright that you cannot trust their parallax. So distance to the massive star is wrong.
I see. The problem is the distance to Sigma Ori, not the surroundings.
Right. Sigma Ori itself, so proper motion, when you look at that, you can sort of trust that, but not the parallax, because it's too bright, they saturate, and they can't really have a good measurement of astrometry.
Right, but if you knew the distance to Sigma Ori from some of these other methods, then could you use the Gaia distances to turn that into a 3-dimensional G0 or no?
Well, the thing is that when you start looking at the uncertainties of that, they're huge. So
they're still too big.
Yeah.
So that's nothing to do with the massive star. That's
it's a lot more than the projected separation. So that's why we stick with the projected separation, unfortunately. Yeah. So we observed the cluster with ALMA observations in this paper from 2023. So here I show you the distance mass of our sample as function of projected separation from the massive star. So basically, the massive star is here. And you can clearly see that inside 0.5 parsecs from Sigma Ori, the disk has really low disk masses. So this is a clear sign of external photoevaporation. You also see that we find this increasing trend of the distance mass with projected separation, which also points to external photoevaporation, also consistent with previous result from Megan's Hansdale 2017. And the very important or interesting thing about this cluster is that you can start looking at the effects of external photoevaporation in the inner regions, but also in the outer parts. You can see that we have this large range of distance masses. We even have some 12 CO detections here. So we can really also study the age effect, because it's an intermediate age cluster in the outer parts. So that makes Sigma Ori a very good region to start looking at these effects. So in order to try to inquire a little bit more about this evolution in this cluster, what we did was start looking at these planes, so the mass accretion versus this mass plane because we know that in the viscous paradigm, these two parameters should directly correlate, and tends to works like the ones in Manara 2023, the PP7 chapter. They have all of this information from different regions, so young regions, less than 10 million year old regions. And we found out that this relation is almost linear. You can see here all the sources for these different regions, but we also get a large scatter on this relationship, and that is still an open question. What is the origin of this scatter that we observe at all ages? But it clearly points to certain particular conditions in this viscous paradigm or framework, but also to the necessity of maybe including a different or additional mechanisms to try to explain these observations. And the important thing about this plane is that we can use this as a proxy of this evolution, because we know that this evolution can be summarized as the mass accreted of the star during the system age divided by the disk mass. So what we did here was use this T-disk parameter, so the disk lifetime, which is just the mass of the disk divided by the mass accretion rate, as a proxy for this evolution. And we did that because some theoretical works, for instance, this Rossotti 2017 work, suggested that we can use this plane to actually confirm or test external photoevaporation in young clusters. So here we show you a cartoon of how this plane can really inform us about the different processes governing this evolution. So if you have a disk that is evolving purely viscously in this plane at a certain age, in this case it's 1 million year, you expect the disk to cluster around this line. However, if there are different processes happening in the system, like internal photoevaporation, planet formation, or episodic accretion that can really break this quasi-state equilibrium driven by viscous evolution, then you expect larger disk lifetime, so populating this lower part of the plane. But external photoevaporation seems to be one of the processes that can actually move the stars in this plane to the opposite side, so to the green part of here, to lower this lifetime. And that is happening because you are removing mass from the outside in, and we know that most of the mass of the disk are in the outer part. So if you externally photoevaporate in a disk, you are removing drastically a lot of mass of the disk, so you move to this part of the plot here. So this plane can really we use it to test if actually external photoevaporation can happen. And that's what we did here.
Okay. Yes. I guess, maybe this is in your planet formation category here, but all of this assumes that the dust evolution doesn't happen and that photoevaporation completely removes that as dust.
Yes, exactly.
Which is obviously right, it's a much more complex picture than that. So I guess I'm wondering about, accounting for things like this spread, either by allowing for differential dust, evolution, or including information from spectral indices, or using CO masses.
Yes.
Like, what happens when you do that?
Yeah, that's a good point, because actually for external photoevaporation, we know that the gas is being photoevaporated with the small dust, but the mass of the disk that we estimate is from ALMA, so it's from the midplane. So that can be also some caveats there. But here, of course, is like a more approximated approach, because we have these global parameters of the disk, and we can have it for surveys of protoplanetary disks. So for now, it's just an approximation that we can actually do that, but definitely having superstructure of different evolution of the dust and the gas can also play a role here.
But there's not enough of these sources that you have CO measurements for, or spectral index information from ALMA that you could line that? Or?
In Sigma Orionis or in more massive regions, I don't really know. For Sigma Orionis, there are really few, and they are in the other part, so they're not that affected by external photoevaporation. Yeah.
Well, we're talking about sources of scatter in your plot. Have you or has anybody else estimated what the anticipated impact would be for episodic accretion history? Because, basically any protostar is expected to have episodic accretion. It's not, we kind of don't. In actual reality, we know that accretion is not a constant process.
Yes.
We definitely treat it that way when it's convenient.
Yes.
But what would be the anticipated impact?
Yes, now people have actually tried to work on that. And what they found is that the variability in accretion can account for some of the scatter, but not like almost 3 orders of magnitude or more from the scatter here. So you need something else, not only variability in accretion. But it's true that it can help a little bit, but not explain everything.
About what magnitude?
For the variability of accretion?
Yeah.
I think that accounts for like an order of magnitude probably.
Typically half an order of magnitude,
Okay.
but it could be up to order of magnitude.
Yes. So we did that for sigma Orionis. So here I show you the results. We use extruder spectra to get the stellar and accretion properties and ALMA observations to the this mass. So we can put the targets here on this plane. And we have 15 targets that have both observations. And this data set has allowed us for the first time to try to test whether this relationship, this plane, can help us really confirm the effects of external operation of protoplanetaries near a massive star. And you can see that the first thing that you can notice is that if these were evolving purely viscously, they should be clustered around here because the cluster is around 3 to 5 million years. But what we found is that most of our targets are here, located here, with shorter deep lifetime. So that might points to external photoevaporation of these sources. But of course, a fair comparison will be to really compare these to other star-forming regions. And that's what I show you here on the gray points. So these are the data from the previous plot from Manara. And you can see that more or less they agree, they populate more or less the same region. So in order to explain these sources with short this lifetime in other star-forming regions, there is this recent work from Zakaria, 2021. And what they find out is that for the other regions that are located here at short this lifetime can be explained mostly by binarity, so multiplicity. So we know that if you have binarity, you can have these truncated disks. So they also have lower masses, and they also push the sources to this part of the plot. So binarity can actually play a role here as well. We don't have much information on multiplicity or binarity in sigma Orionis, but I highlighted here with an additional center point, the sources that have high Rube parameter. So we know that this parameter from Gaia, which is larger than 1.4, it might point to multiplicity. And it's interesting to see that most of these targets are actually here in shorter this lifetime. So binarity can play a role, but we need to follow up on this to see if there's actually can explain everything. But in order to test whether these shorter this lifetime are actually related to environmental factors, so to the massive star at the center, here I show you the this lifetime and on the y-axis as a function of projected separation. Because if we expect that actually the environment plays a role here, we should expect to have like a trend with projected separation of this lifetime. And as you can see, what we found is that indeed sources that are closer, so within 0.5 parsecs, really have very low this lifetime, less than 0.5 million years. And we also kind of see like a potential trend, increasing trend with a projected separation. But of course, you can argue that what happens with these sources over here that are beyond 1 parsec and also have very low this lifetime. Well, we checked those, and these are in fact outliers. So most of them are foreground objects or etch-on disks or very high accretors or even possible binaries. So all of these points to environmental factors affecting at some point sigma Orionis. So with this in mind, what we want to do is really go and try to characterize the winds that are supposed to be happening if external photoevaporation is actually at in this cluster. So we went to study the wind diagnostic, so the optical forbidden lines, and for that we observed this cluster at high resolution with Mike in Las Campanas Observatory. So we have a sample of almost 30 classical T30 stars there, and the idea is to just study the forbidden lines. So this work was motivated by this previous work from Rigliaco, 2009, where they find this external photoevaporating this candidate in the cluster. So this is this source, 587, located at 0.3 parsecs in projected distance from sigma Ori. And what they found is that they found that this source is very bright in these high ionizing species. So the nitrogen and the sulfur too, they found that this line is blue shifted and also asymmetric, which is what you expect from a photooperated. So they claim that this might be a external photooperated protoplanetary disk in the cluster. So we went there and observed with Mike using this high resolution spectra. And here I show you the results for the oxygen 1 line at 16300 for the detected sources. And you can see that we have very different morphologies of the line. We have different Gaussian components. We feed the line with different Gaussian components. And you can see that some of them have, a lot of them have high velocity component, also low velocity component, broad and narrow. And also some of them are just single component lines. So the idea now, I mean, this is preliminary results. We're still working on data, but what we wanted to do was analyze the kinematic properties of the line. This is the low velocity component of the oxygen 1 for sigma Ori. So again, this is the full Big maximum as a function of peak velocity. And you can see that we have lines that are composed of narrow and broad component, which is the light blue and the red, and also single components. But the interesting thing here is to compare this with younger or older regions. So here I compare with the sample of Asante, 2019, so 1 to 2 million years more or less. And you can see that they more or less agree. They have broad, narrow, single. But the striking thing is when you start comparing with older regions. So you can clearly see this is Upper Scorpion now from the sample of Fan last year. And you can clearly see the difference. You really lose the broad component and you get a lot more single components here. And that this is more striking when you do some X statistics. So here I show you just the frequency of the different components. Sigma Ori is here at the center. So you can see that for the younger regions here, they usually have less frequent single component as compared to the narrow and broad components. That is the purple color here. And you can clearly see that sigma Orionis seems to be in a really intermediate stage. Just as the age of the cluster, where they have almost 50-50 between the single component and the narrow components. And actually, Upper Scorpion is mainly single component for the oxygen 1 line. So it's very interesting that we can actually see these changes on the oxygen 1 line with this evolution by looking at these forbidden lines. So that is very, very interesting.
So I'm wondering why you use a Taurus and Lupus if you didn't use Orion ONC instead. Because the Taurus and Lupus doesn't really have external photoevaporation. That is, some of the really large ones they do, but most of them don't.
Yeah.
So that might be another reason for the difference.
Yeah, that's true. I can also compare with the ONC. I don't know how much of a sample there is, number, statistic.
Yeah, it's very hard to get oxygen because of nebulosity, and it's extremely challenging to get data. So I'm sure that's why you used the Taurus.
Yeah, because
survey data for that.
Yeah.
So in FANG, we actually looked at the intermediate region as well. So I think the statistics are similar. But then this makes me wonder if this is all internal operation.
Yes.
You know what? I have my spectra for 1977, and I have to talk to you about it because I wonder how much is internal, how much is external.
Yeah, definitely you can have both. Processes.
Can I have another question about Upper Sco? So either Alaria or Nixon probably has a better memory, but we recently were at a workshop and we heard a talk about how there's a wide age distribution Upper Sco.
That's right.
Yeah.
We didn't check that.
But that's why
Mean FANG was my post.
It was mean fun. Okay, mean fun.
Yeah.
So when comparing with Upper Sco, one should see what sources you're choosing and whether or not they are actually that age.
Yeah, we should.
Because they may not be. And so you could get very.
That's the problem with Upper Sco.
But this was like, you're like, this is a very clear gradient now that they have been able to say like, oh, okay, here's the.
Yeah, that paper was not out at that time.
Right, no, I know, yeah. I'm not agree with you. I go to panel before, right? We've all written papers about Upper Sco having a given age, but now we're just up.
I agree.
So.
Yeah.
There have been always a group.
I don't know if this is from the 2023 or the INPREP, but if it's from the INPREP, then there's a chance to.
Yeah, no, I think it's important.
Yeah. But it definitely can be internal photoevaporation as well. But if we really believe that it's an environmental factor, we should also see a difference with projected separation. And that's what we did here. So I show you here the full width maximum of the oxygen one low velocity component here and the peak velocity in the bottom as a function of projected separation. And very interesting, what we found is that all the targets that are within like 0.7, 0.8 parsecs in projected separation from sigma Ori actually show a single component in the oxygen one line. Further out, you can see different variations there, but it's interesting that these targets here clearly are different from the rest. So external photoevaporation is changing something there. Maybe the outside-in depletion produces a similar effect like a later evolutionary stage because the disk gets lower in mass. But this is definitely something very interesting that we are still working on and looking on. But I would love to have feedback from you experts and try to understand this. But this is what we found. It was unexpected. I just did the fits and then I just plotted and I said, wow, all of these are just single components. So that's very interesting.
I will say on
the center. So it's not clear that it's flowing, right?
Yes, exactly. Yeah. But I mean, if you have the predictions from I think Julia Valladio that also do these standard photoevaporation models, they seem that they seem to be really low velocities for the photooperating winds. Yes.
I will say when you were showing your plot of lifetime versus projected separation, there seems to be a very similar difference between your sources in the lower left quadrant and the lower right quadrant. I know you were speaking of it as kind of one overall trend, but it kind of looked like two separate populations to me. And so I think you might, if you're looking for next steps of exploration.
Oh yeah, well, definitely.
I think your idea of maybe these are essentially being forced into later stage evolution because they're so close. And I would guess that there's a hard distance cutoff. It looks like there's a hard distance cutoff where you're.
Yes, definitely. No, yeah, we're trying to get observations, follow observations of Orionis. I mean, I know that for ALMA, there's Jane 1 that has very nice data from Orionis, so I have to wait for that to be published. But also we are interested in follow-up Orionis with UVES, with high resolution spectroscopy as well, to try to get other lines that can give us some clue. And I mean, also getting like images, even Hubble or MUSE, it's hard, but we're gonna try.
BLA?
Oh, well, that's also a possibility to just try to complement the ALMA observations with the BLA. That's also a very good point, yeah.
So if you, did Megan, the new paper from ARMA, do they have a size measurement for the disks?
We didn't do that.
Because, if you could do that, you could actually correlate that one also from the distance to the size of the disk.
Yes, that definitely.
And another thing that I would like to point out, because is that in ONC, they moved around, the massive stars moved with other YSOs that being photoevaporated together. But then the one I'm working on, the B star actually moved in.
Yes.
They had a different promotion. Then it will affect differently actually for the disks.
Yes.
So checking, I think it may be really, because sigma Ori is multiple system is really hard, but you could still check over longer time. The promotion of sigma Ori might be very.
We try to check that, but the problem is that for the massive stars or sigma Ori, it comes from Hipparcos, and it seems like to be like another good.
So what you could probably do is go from very old data onto recent data and then collect more data and then actually get astrometry yourself, basically.
Okay.
With over longer period of time.
Yeah, that's definitely something that
would be interesting.
Yes, that's definitely true. I think.
Could you remind me what was the G0 at 0.7?
What?
G0 of this border of 0.7 parsec or whatever was it?
At 0.7 parsecs?
Like when you see this difference in the components.
Yeah, well, you can see that it's around like 10 to the.
About 1,000.
Like, 2 to the 3. Yep. So that is very interesting and very cool that we can see these changes by external photoevaporation, just looking at the oxygen line. So we are now looking in the other lines, so the nitrogen and the sulfur 2 lines that we also have access to with Mike. And it's going to be very interesting to see what we found there. But there's lower detections, but let's see. But of course, the ideal case would be to actually go and especially resolve this line. And for that, we now can do that using this amazing instrument MUSE. So we did that. This is a work led by Mari Liz Aru at ESO. It's a PhD student working with Carlo and with me. And what we did was observe with MUSE a sample of 12 proplyds in the ONC, as you can see here. We have all these proplyds affected by θ1 ODC, and also these two. This is the Tom and Serena proplyds here, and also these giant proplyds, which is an outlier in all of our data. Is huge, and we believe that is affected by θ2 ODA, but probably also by this one. But we have this beautiful data set where we can actually start looking not only about the spectral information, but also the spatial information. So we know that proplyds have this cometary morphology because of the interaction with the high energy radiation from the massive stars, and they produce this thermal wind, the neutral outflowing gas that then gets ionized as it expands and interacts with this high radiation. But now we are in a very good position of not actually having a sketch of the proplyd, but actually look at them and actually see the different structure of the proplyd. And this just shows the power of MUSE observations, where you can actually see the different structure of the proplyd at different wavelengths. So you can see how these ionization structure and properties change at different lines. So we have these optical forbidden lines of nitrogen, oxygen. You can see here that it was work from King-1 last year, where they focus on only on the jet of this proplyd, the huge proplyd. But it's amazing how this data set can now give you a lot of more information on where these lines are coming from. And that would help also to try to interpret just spectra, just as the sigma order that we have. So we can now really have a holistic view of what is happening in the system. So you can see that the structure of the proplyd changed a lot during all these wavelength ranges. And of course, you can now just put it all together and have this beautiful image that we love. So it's an amazing data set that we now have. And for this particular work, that's what just out last week, I believe. So it's very recent. We just wanted to show the morphology of the 12 proplyds that we have in the different emission lines, 7 emission lines, and also measure the ionization front of this. So the ionization front is this bright part here, pointing towards the ionizing star. And one thing that we notice is that, for instance, this sulfur 2 line here that is usually related to jets as well is really good tracing the tail of the proplyd. And that is more or less common for all of the proplyds that we found. So that shows just the power of really go and especially resolve the lines so you can understand where the lines are coming from. So that is very nice and beautiful data. So for the measurement of the ionization front, I know a lot of people have also done this for the Orion proplyds. In this case, we just put the location of the ionization front in these bright cups. So the peak of emission here. So we did a radial cut of the intensity profile of the proplyd in this direction, pointing to the ionizing star. You can see here on the bottom, the star should be here at 0. So this peak of emission is the ionization front. So we did that with this data set. We estimated the ionization front in 4 different emission lines. And here I show you the results. So this is the ionization front radius as a function of projected separation for our proplyds. And what you can see in all of them is that we found this increasing trend of ionization front sizes with projected separation as expected from external photoevaporation. We can even use the prescription for the H-alpha line to also get some estimate of the mass loss rate from the ionization front radius. And I will talk about that in a few minutes. But you can clearly see this trend. And of course, this is not the only work that have done this. We have this work from Serena in 2016, where they also estimated the ionization front radius from proplyds in NGC 1977. And it's interesting because they prove lower higher FUV field strength for these proplyds, and it's more or less here. So it's proving this part of the plot, and they consistently found larger ionization front radius. So 4.4 to 0.7. So it's going to be like over here. So you see that is consistent with external photoevaporation, where you have larger and larger ionization front as far as you go further and further for the ionization star. So in order to know a little bit more about the level of ionization, what we can do is try to use the ratios of ionization front sizes in different lines. And what we found was very interesting because you can see here, this is the ratio of the oxygen 3 ionization front radius as a function of the oxygen 1. And as expected from the ionization stratification, the most ionized part of the flow, so this line over here, highly ionized oxygen, is located closest to the UV source. So you can see that the mean of the emission is a little bit higher than for the oxygen 2. Of course, we have this uncertainty, so we still have like a consistency there. We need more observations in order to really clearly see this effect. But one thing that is very interesting is that even using the H-alpha line compared to the oxygen's lines, you can clearly see that this distribution is almost flat for all of these ratios of ionization front sizes. And that is what it's telling us or pointing to is that it seems like the ratio of these ionization front radii scale in the same way for all the proplyds, regardless of the incident radiation. So this stratification, ionizing stratification in the proplyds seems to be self-similar. And that is something also very interesting that we found. Even this giant proplyd that seems to be like an outlier in every plot is this one here. So it seems that even though it's larger, the relative sizes of the ionization front of different lines seems to scale the same way.
So the ionization front size actually used by modelers to estimate the mass loss rate because of that.
Yes.
It traces that way.
Yes, and
when the mass loss rate is higher or not, depending on G naught, obviously, and the distance. So
I'm totally confused. What is the conclusion that the ratio of ionization front sizes at different ionization states is self-similar?
Yeah, so the relative sizes of the ionization front, for instance, from the H-alpha and then the oxygen 1, oxygen 2, oxygen 3, these relative sizes for all the proplyds scale the same. So even if you have a proplyd that has a lower FUV field, these relative sizes of the different radius of ionization for different lines is going to be the same.
But all you're showing is that the ratio is fixed, not that it's self-similar usually implies that
the ratio is fixed, basically.
but that's not the same as self-similar, right? That's what
It is not, yeah. It's not
self-similar
that.
means something that you can, make non-dimensional in terms of time or something, or some other variable, and it will expand. So for that to be self-similar, you need to show a trend in one of them, and that the trend was the same in both. But that's not.
It's constant.
It's just constant.
It's just the line ratios are constant.
Right, independent of size.
You said the size of
Yes.
it.
Right.
The size of the different regions.
The size, yeah. The relative size of the ionization fronts of these different lines is the one that is the same.
But it doesn't have self-similar would imply there is an underlying scaling with some other variable that you're aware of. But I think that is not yet discovered, which it could be.
Yeah.
There could be, yeah.
There could well be, that
There
could be. Otherwise, but so I guess, could you give us a little sense of what you would expect? You're presenting this as surprising that they are the same.
Yeah, well, at the end, it's not that surprising.
Okay.
I can show you after in the backups, but mainly these ionization front ratios will mainly depend on physical constants. So it should not depend on the distance. That is something that we realized looking at this plot, and then we start looking. We have a little section in the paper also talking about this, but at the end, it will only depend on the recombination coefficient and also the ionizing, not the ionizing radiation. Yeah, the number of photons. So,
So they're probing the same, right? You're probing the same material, so just get a different.
yeah.
Naman, you have a question. Would you like to speak up?
Oh, I didn't want to interrupt the discussion here. Maybe I can ask at the end.
Yeah, you can. Yes.
Okay.
Yeah. Okay. So as Serena was saying, thanks using the size of the ionization front, specifically for the H-alpha line, in this case, we can estimate the mass loss rate. So this is the results from the mass loss rate of our sample as a function of the FUV radiation. And you can see here on the top also the projected separation, and it's inverse, as you can see, because we are showing is the UV radiation field here. So you can see that as expected, as Serena was saying, the properties that are closer to the ionizing star usually has also larger mass loss rate. And we also see like this trend that is also consistent with external photoevaporation models. And we found no dependencies of these with the stellar mass. And also we found mass loss rate in the range of 1 to almost 110 to the 7th solar masses per year. And this is also consistent with other works. We see that these proplyds that has this high level of FUV radiations of 10 to the 7th and to the 6th have higher mass loss rate than, for instance, in NGC 1977, which is a lower G0 environment, and they have a lower mass loss rate, and also slightly higher than the NGC 2024 that also is around here. So, and that is also consistent with this other previous work from Tom and Serena. So finally, using this mass loss rate and combining it with recent observations of ALMA of these proplyds from Nick Ballering last year and also MAN 2014. So we have 4 proplyds that have ALMA observations and also mass loss rate estimated by us. So I show you here the mass loss rate as a function of this mass. So this is similar to the one that I showed you from Sigma Ori, but this is more like a photoevaporative time scale. And you can see that for the 4 proplyds that we have, the different colors here are just a different prescription for the temperature of the dust in order to estimate the mass. We see that these are really short this lifetime, so less than 0.1 in a year. So the proplyd lifetime problem remains in this data set as consistent with similar works from in different regions from Tom and also Serena. So it's very peculiar that we actually see in these proplyds just in the time where they are dispersing. And of course, we know different approaches of how to deal with this problem. It might be by shielding of the gas, and these are just the sources that are just being external photoevaporated. Can also be optically thick emission from ALMA, so we are underestimating the mass, or can also be the kinematics, how long these proplyds really are being close to the massive stars, and also new generation of stars, and probably these are just the youngest ones, which are also the massive ones. So, but this is very interesting and just show how using this data set can really be a benchmark for then go and study more massive star forming regions like Karina, like the work that Domi is doing, where you cannot really discriminate between the ionization front and the disk, where you have all combined. So we can actually start looking at these data and try to understand that better. So that was all that I want to show you here today. So here I show you my conclusions. And if you have any questions, I will be really happy to answer any. Thank you.
Okay, so now on your chance to first question.
Thank you. Great talk. Thank you so much. And those images were really beautiful. I was wondering, could you please expand a little bit on why you said that internal photoevaporation would increase the disk lifetime and external photoevaporation would decrease? Because I believe both are removing masses from the disk. So I would expect the same effect.
Yeah, that's a good point. I was trying to look at that myself when I look at this theoretical prescription. And why I found what I could understand is that in these type of models that they use, what they do is that they evolve the disk viscously. So basically the disk is expanding while they are evolving viscously. So you can have internal photoevaporation or planet or episodic accretion, and this will evolve, will expand, and that increase the mass of the disk, because the prescription that we have for the mass of the disk is like if you have is a linear or direct relationship with the mass. So if you have a larger disk, you have a more massive disk, and that's why they move to this part of the plot there. In contrast to external photoevaporation, where you remove the mass, so you move it to the other side.
Okay, so in case if the disk is evolving with MHD winds, not viscously, then this would not be the case. Then this would be the opposite.
Yes,
okay.
Yeah.
And my second question was, can this idea or something else be used to estimate how much is the contribution from internal versus external photoevaporation in any given disk using any of these lines? Because I believe both are happening at the same time, right?
Yes, definitely. No, yeah, that's the main motivation behind these MUSE observations, and that's mainly the work of the PhD, the idealized goal final goal of the PhD of Mari Aru, where we can actually say how can we discriminate between internal and external photoevaporation. But right now we don't really know. We are just looking at the data. But we hope that we can at least move forward to that goal. But that have to be something very important, because if we want to study these more massive regions, we need to know that. But right now we don't know.
But the
Thank you
MUSE
so much.
data is really amazing. I'm so jealous because they could actually see that there was a photoevaporating, externally photoevaporating this gas as an image, not as line. And you know where it's coming from, like, wow.
Yes, it is.
Yeah.
So actually, can you go back to the plot of the extruder and the
Yes.
accommodator with the that one?
Okay.
Yeah, this one, okay. So I look at this plot and I think probably you should stop plotting diagonal lines on it. Like, I can't see when I see this, they're like, and I guess the problem is that then, right, you're using those diagonal lines, which don't seem to really fit the data.
Yeah.
To then create an x-axis or the y-axis in your next plot.
Yeah.
Like, what can we do that's, I mean, now that you have such amazing data, like, can we do better than using what is obviously not the correct disk lifetime? But it just seems like clearly, I mean, the dust mass is not the, I mean.
Yeah.
Yeah.
I think
That's the
nice.
motivation of
Good.
having now this beautiful data set, because this is what we have, right? From
Right, but I mean, but you have this beautiful, even saying that the dust mass is not the right proxy, you still have the data. But like, what else can you do with that data than turn it into a disk lifetime? Like, there must be more, like, like, is there something else you can do with it to, you know, draw conclusions about internal versus external photoevaporation rather than just using that as a way to calculate a number that's probably not, as you've shown, a good representation of what's going on. I mean, I don't know the answer, it's just,
If we have many more of the gas disks, to mass data, that would be good.
I think the problem of the disk lifetime in mass star computation was pointed out long ago.
Oh yeah.
So and probably, I mean, we'll find the same, I think.
There's a
Maybe
trend,
the reason-
yes,
but I
there's
mean,
definitely known trend.
But maybe the reason is that, you know, the projected separation you see today was not always that separation.
That's true, that's true, especially, I was thinking,
Didn't talk with the movie of the.
so I showed you, right,
Yeah,
the
yeah.
nineteen
It's
seventy-seven,
amazing.
so yeah, it's, the wires was moving this way.
Yeah.
But then this V-star was moving this way. So that explained actually lifetime, but it doesn't explain it ONC because they were together. It's evolving together with wires. So we don't, there's too complex. I don't know what the hell is going on with those.
Yeah. No, what people usually say is that they have multiple generations of the stars.
Right, multiple
These are-
generation stars and also shielding.
But
Yeah.
yeah, I mean, but again, all of that, but I guess the thing that I'm worried about is that all of the need to come up with these excuses is based on an estimate of T-disk that probably is inaccurate.
Yeah,
So,
I
like,
mean,
instead of worrying about solving the problem with the disk lifetime, why not say, well, maybe this is not a good estimate of the disk lifetime?
so that's what we have, I guess.
Right, I guess, but I mean, that's not the way it's presented, right? Being presented,
Right,
like,
right.
how do we solve the disk lifetime problem rather than, this is a bad way of measuring disk lifetime?
No,
What
yeah.
else can we learn instead,
Yeah.
right? Like, that's sort of,
Yeah.
that's the big distinction. It's because people, it's like, it's not that people don't know that there are oversimplifications, but yet it's still the way that the data is referenced.
It's very hard. So the theorist like Andrew Winter has a paper on appropriate lifetime problem.
Yes.
Kind of. And then like Carlo and your group and everybody is trying to figure that out. It's a mess, I have to say.
But I mean, measuring masses in this is really hard.
Especially gas mass.
Yeah, the gas mass particularly.
Sure, but now that you have this MUSE data, I mean, I guess
It'll be
it seems like
good.
there's lots of other interesting things.
Oh,
that
yeah.
you can
Oh, yeah.
learn
We're
about
just
the
deep in, in the
processes.
surface, of the data set. So let's,
Yeah, so the MUSE data set is so amazing.
yeah, it is.
A lot more will come out.
Yeah, I love this. Okay. I will just leave that.
Yeah.
Yeah, it's
Would it be possible for MUSE to like resolve one of the largest disks where all this outflow comes from this? Like at least we know from, is it from the outer disk or the inner part of the disk?
Yeah, that's usually a question that I usually get, but I think it's not enough to discriminate. I mean, not even in the giant proplyid here, which is the one that we have more of a chance of trying to especially resolve this. If we believe that this, well, I think it's better here. If we believe that this is actually the disks, because we're not sure, it might be also like a halo around the disk. We're not sure. We cannot really have the resolution to discriminate what's happening inside in the inner part compared to the outer part. I mean, these disks are usually very compact because of external photoevaporation, so it's not that easy.
Yeah, so there are some of the lines that you can visualize with ALMA and that, and
Yeah.
those are not on the disk, but they're evaporated away from disk already, so they're around the disk.
Yeah, and that's a good point. Like, go and observe it.
That's expected in a way by theorists.
Yes.
And so I'm sure there will be paper fitting that for that kind of bubble or oxygen line above the disk.
Yes.
But we're lucky enough to have one of the largest disks around in this kind of region. So
Yeah.
we can at least, but we don't. At least
There are some large disks, even in ONC, when they go away from the massive star, their GNOT drops down dramatically to 1,000, and they still have a large disk.
Quickly, I noticed that you don't have many jets in Sigma Ori. Is that consistent with the age, or is there a difference in right, the MHD, for instance, with the jet connection in this one?
Yeah, that's a good point. We have a few, but not that much high velocity components in Sigma Orionis. I haven't really checked if that can be like related to other properties of the cluster, like age or even accretion. So that will be a very good check that I can do, and how that compared to younger ones. Yeah.
Older ones.
Yeah.
Yeah.
Exactly.
It's very important life between 3 to 5 million years.
Yes. Yeah, that's a good point. I will check that. Thank you.
There are much fewer jet sources. I'd like to hear that, what fraction of them actually have jet.
Okay. Yeah, I will check that.
That'll be great.
And we can discuss. Yeah, definitely.
This is beautiful data. Anybody else have a question? So I will stop recording here. Thank you again for Karina. But then we have lunch